Hello and welcome to Tonight at 8 from the RSGB. The GB3 Meteor beacon has been live since May 2022 and has enabled studies of meteor events by amateur astronomers and radio amateurs, as well as being a wonderful educational resource enabling many STEM-based projects to take place. Now the project is entering a new second phase, which involves developing a network of receivers to enable detailed studies of individual meteor events to take place. And tonight we're very pleased to welcome back Brian Coleman, G4NNS, to tell us more about this new development. Welcome to Tonight at 8, Brian. Can you briefly tell us what you'll be covering this evening?
Yes, I shall start with a brief description of the project for those not familiar with it, and go on to talk about the fundamentals of radio echoes as observed at 6 metre wavelength, and describe how we can use waterfall displays to observe and analyse echoes. And then I'll go on to talk about where the project is heading in terms of future developments and providing data for the study of meteors.
Wonderful. We're looking forward to it, Brian. And if you at home are watching this on Monday the 2nd of September, then this is live and you can ask questions or make comments on either YouTube chat or BATC messaging at any time during the presentation or straight afterwards. Please include your first name and call sign if you have one within every message. And note that you can make this video stream fill your screen on most devices, usually by double clicking on the picture or pressing the full screen button. So now let's go back to Brian to find out more about the new developments on the Meteor Beacon project.
Okay, thank you, David. The first phase of the project has been to build the beacon to illuminate the sky where meteors burn up over the UK, and this is very much a citizen science project, which is a collaboration between the worlds of amateur radio and radio astronomy, and it's been supported by the RSGB Legacy Fund at the capital costs, and the running costs are being supported by the British Astronomical Association. Meteors, when they enter the Earth's atmosphere, burn up at an altitude of about 80 to 100 kilometres, as in this diagram here, the big blue line. And when they do so, they create intense ionisation that is reflective to radio. This happens, as I say, at about 80 to 100 kilometres up. There's a fascination with meteors in the public generally. Shooting stars, very fascinating, and it gives us an opportunity to interest people in radio and astronomy while we build this, what is in effect a radar system for research into meteors and their interaction with the ionosphere. Meteors deliver a variety of atoms, so they're of interest to us in the radio community in particular. So our first priority was to build the transmitter to illuminate the sky, illuminate the region where the meteors burn up. So a beacon transmitter was constructed. A power amplifier capable of producing a continuous output of around 100 watts was designed by Andy, G4NNS, while a control and monitoring system based on a Raspberry Pi was developed with help from Dave, G8GKQ, and with software by Heather, M0HMO. And as was said earlier, the beacon has been operating since May 2022. I should perhaps explain at this point that in the radio community we tend to refer to each other by our first name and a call sign. So those of you from the astronomy community who may be watching this when we're talking about Dave, G8GKQ. G8GKQ is Dave's call sign, which is unique, and it's the way that we can uniquely refer to one another without going into too many details. If you visit the Beacon website, which is ukmeteorbeacon.org, you will find a button there you can press, which will take you to the status of the beacon, and it is show you its power level, and you can confirm that it is indeed on. If you're not hearing any echoes, perhaps a good idea to check that the transmitter is functioning. It's been highly reliable, so it's usually on, and you can simply check it by going to that page. The beacon is located at the Sherwood Observatory of the Mansfield and Sutton Astronomical Society. That's a fairly central location, which ensures that we're illuminating a large proportion of the sky over the UK. This picture was taken at the time of installation. The site looks quite different now because major building works are going on to develop the site into a science centre. So it's very nice that we have the beacon located at what will be a really good science centre. Unlike conventional propagation beacons, GB3MBA beams vertically upwards. And to overcome losses due to cross-polarization with and this is achieved by using two Moxon type antennas with a 90-degree phase shift to create the right-hand circular polarization. Also, the Moxon design has a very high front-to-back ratio, which is good. It means that no ground plane is required and very little power is wasted into the ground. Inexpensive software-defined radios with a simple wired dipole antenna will receive echoes from GB3MBA throughout the UK and beyond. And this makes building a Meteor echo receiver a great STEM project, introducing radio and astronomy. And the potential for this project for creating great STEM projects was recognised very early on. While I suggest in this slide that a dipole is sufficient, a directional antenna is better. And here is a rather Heath Robinson version of the Moxon antenna, which has the advantage it's directional, so you can point it up into the sky where the echoes are coming from. You can use it to null out noise, and it's a better solution than the dipole. And there is an excellent article on how to build this, build these antennas using materials that are available readily from most DIY stores. So I commend that particular antenna design. When it's built properly out of aluminium tube, it's also very robust and it's reasonably compact. So when we receive these echoes using software-defined radio, it's normal to display them on a waterfall display, and this can be done using software available free, such as software SDR console, and we can then see the echoes in great detail, which we'll talk about a little bit more as we go through this evening. In a waterfall display, many of you will be familiar with this, but for those of you who are not, the display has frequency as the horizontal scale, and in the center is the frequency of the beacon at 50.408 megahertz. Time flows downwards, so hence the name waterfall display. The strength of the echo, the brightness of the echo, if you like, is displayed by the brightness on the display. So time is vertical, frequency is horizontal, and we can see from here that this echo has two distinct components, of which more in a moment. Accurate display of the echo frequency shows us the Doppler shift due to the changing reflection path length as the meteor decelerates due to friction with the atmosphere. Meteor echoes typically have two main components: the head echo, which exhibits rapidly changing Doppler shift as the reflection path length changes and the meteor decelerates. That's this little horizontal line, excuse me. As I said before, time is flowing downwards, so the time that this head echo lasts is very short, typically only of the order of 100 milliseconds or less. The tail echo is this fuzzy bit that extends upwards, and that can last much longer. This is from ionization remaining after the meteor has passed through a region of the ionosphere. And reflections from this longer lasting ionization can be used to extend radio range at VHF, a mode of communications known as meteor scatter. What Doppler shift there is in the tail is due to wind speed at the altitude where the ionization is suspended. So the two components, the head, rapidly changing Doppler shift, appears as a nearly horizontal line on a waterfall display, and the tail, where it exists, as a vertical fuzzy line. That's representing spectral spreading. Excuse me. Here's a more detailed diagram showing the description I've been giving. The head echo with a very short time scale and a big change in frequency, and the tail echo fairly constant, slightly spectrally spread, which can last for minutes, sometimes seconds to minutes, but doesn't always appear. We don't always see a tail echo. The shape of the reflective ionization that forms as a meteor burns up has been described as like a tadpole. And this diagram here shows what I'm talking about. The head, if we like, and it's unfortunate that we use the term head and head echo. We're talking about slightly different things. The front, if you like, of the meteor, where there is intense friction and intense ionization, and that is too small, typically, if we're talking about small meteors, typically the size of grains of sand, and that region is likely to be too small in radar cross-section to be reflective, significantly reflective at 50 megahertz. At higher frequencies, that may not be the case, and it may be that it reflects. What happens is that the ionization extends behind the meteor. The ionization electron density quickly drops due to recombination, but the effective reflecting length of it depends on frequency. At 6 meters, a lower electron density is required than at, for example, 150 megahertz. The frequency of the Graves radar, 143 megahertz, for example. That tail may be significantly shorter, and therefore not play a major part in the reflection. So that the blue part highlighted in light blue is the ionization that remains just for a few milliseconds behind the meteor, but it's moving so fast that effectively it creates a cylindrical area of ionization, so the tail is a bit like a rod or a wire. As I said earlier, 60 megahertz requires a lower electron density for reflection to occur than shorter wavelengths, such as the 2 meter wavelength of the Graves radar. So at 6 meters, the rod or wire-like reflector appears longer than at shorter wavelengths and becomes the main reflecting medium for small meteors at any rate. Now, if you think of a wire hanging in space, this is really what we're talking about as the meteor burns up. This is flying through the atmosphere at great speed, and the wire will radiate just as a wire antenna would. A rod or a wire is effectively a badly terminated antenna. It will pick up energy from the right-hand circular polarization that is illuminating it, and it will re-radiate it with linear polarization aligned with the meteor's trajectory. The polar plot of the re-radiated signal will depend on the length of the ionized tail. If it's a half wavelength long, it will produce a nice donut-shaped polar diagram. If it's longer, it will begin to produce multiple lobes due to interference. Depending on whether the transmitter or receiver is in a peak or a null, the echo will be more or less strong. Also, the echo could be cross-polarized with the receiving antenna, creating more loss of signal. So it's possible for the transmitter or any of the receivers to be in a deep null in the radiation pattern and so not see the echo. This is the highly directional nature of meteor echoes, or echoes from small meteors at any rate, at 6 meters. And an early ambition of our project had been to calculate the location, the radiant and trajectory of meteors using bistatic radar techniques. But it has become apparent that, at least with small meteors, this is not as simple as it sounds. This is due to the highly directional and polarized nature of head echoes. We need to see the same head echo from multiple directions in order for this technique to work, for us to triangulate and calculate the radiant from which, the direction from which the meteor has come, and its trajectory to where, if it's, for example, big enough to land as a meteorite, where it might be found. It may be that when we have data on larger meteor events that this is less of a problem. Here's a fairly classic meteor echo as seen on a waterfall display to explain some of the other bits and pieces going on. In this example, we've got a bit of a direct signal from the beacon according to propagation conditions. If you're within 200 or 300 kilometers of the beacon, you will see some direct signal. There's also some faint aircraft echoes here, and this could be some interference of some kind, but this is a very distinct head echo, which extends in this case out to about 250 or more hertz, so plus 250 hertz Doppler shift at the start, and at the end it's sort of minus 50 hertz of Doppler shift, and that all happens just in a few tens of milliseconds. So, while anyone can make their own receiver to study meteor echoes from the beacon, and we hope that many will do so as a great STEM project, phase 2 of the project has been to develop a network of web-based receivers accessible to all to study meteors. And by having them distributed around suitably, we have a range of different reflection geometries, so we should capture as many echoes as possible. This is the 6-screen display which we have running. If you visit the project website at ukmeteorbeacon.org, you'll find a button labelled live stream, I think it is. If you click on that, you should see something like this. Currently we have up to 6 receivers in the network, and their echoes are displayed here. At the moment we have one receiver is down in Devon at the Norman Lockyer Observatory. One is near Armagh in Northern Ireland, not far from the Armagh Observatory. At the moment, 3 of the receivers are currently located at my location. They're awaiting suitable sites to be distributed to. And we have one receiver that's operating from a private location in Malvern, near Malvern in Worcestershire. So at the moment we don't have the best reflection geometry, but we're working on it. What is interesting here with the 2 receivers at my location is we have one of them horizontally polarized and one vertically polarized, and you can see that they do not necessarily see the same echoes due to cross-polarization. You will see here quite a few aircraft echoes going on, bit of direct signal, strong direct signal at Malvern, for example, and aircraft echoes at the various other locations. In this particular time, the 6th receiver, which is actually not at this latitude and longitude, it's at my location, is pointing vertically up, whereas the other two antennas are pointing roughly to the point 100 kilometers above the beacon. This map gives some insight into the receiver coverage. The lines actually represent roughly the 3 dB points where the signal power is down by a half or 3 dBs. So we're covering quite a large range of the country. In fact, we're covering a much bigger area than that at slightly reduced signal strength. Echoes from meteors above the 400 kilometer diameter region covered by the beacon, echoes can be heard and detected quite easily out to about 1,000 or 1,200 kilometers. So it would be nice to have some receivers even further away in the future. The network receivers are based on the RSPDX software-defined radio from SDR Play, and it's controlled by a Raspberry Pi 4. The RSPDX is frequency locked using a GPS reference so that precision Doppler measurements can be made. This is the block diagram. Here's the RSPDX. The main antenna comes in via a coupler, which I'll come back to in a minute, into the RSPDX. The GPS antenna is split two ways. One way drives the Leo-Bodnar frequency reference to make sure that we're locked on frequency, and the second receiver is in a module designed by Andy G at G4NNS, which generates timing pulses, which I'll talk about in a moment. These are to correct for latency through the processing and across the internet. The network receivers stream their data to a central server in what is an IQ format, not dissimilar to a .wav format. So they are streaming about 10 kilohertz, I think it is at the moment, 10 kilohertz of data from each receiver. You can see again the path here of the into the timing module, where a signal is generated, in fact, 2 kilohertz away from the beacon frequency, and that is coupled at low level into the input of the receiver so that the timing marks have to pass right through the system. Here is a view inside one of the prototypes. We've built 5 or 6 prototypes so far. Starting at the bottom, the antenna, 50 megahertz antenna, comes in here. Here's the coupler injecting the timing signal. Here's the SDR Play. Here is a splitter for the GPS signal, which splits it into the Leo-Bodnar reference and the G4NNS timing module. Over here is the Raspberry Pi, and here's the power supply. So here, with a slightly wider bandwidth than we can show on the 6-screen display, it is a shot with plus and minus 2.5 kilohertz of band shown, and these marks on the left are the timing marks. The leading edge of those timing marks, that's the bottom edge of them, is synchronized to UTC within a few milliseconds. And by injecting the signals at that point, it means that the data that we stream can be correlated with precision, the data from different receivers, and in the future with correlated with optical observations, of course, which will be very important. The timing marks also encrypt some additional data by the length of the pulses in the timing marks over a period of a minute. So the project has got to the stage now where we have in place the transmitter. We have a number of receivers. We have a central server to which the receivers are streaming their data, and the central server provides the 6-screen display. It has relatively low bandwidth, but nonetheless it shows us all sorts of interesting echo shapes, which I'll go into in a little more detail in a moment. The objective at the end of phase 2 is that we also have full bandwidth data available from all the receivers, which we can use for research, or can be used but for research, serious research. The full bandwidth data includes the timing and much more data on the signal levels and so on, which means that the head echoes can be analysed in much more detail. This with the objective of moving towards being able to triangulate the echoes. So here's an example of the 6-screen display. One of the receivers is not operating, as you see, but the purpose of this particular slide is to show the very directional nature of the echoes. In this example, the Northwest Hampshire receiver has seen 3 echoes quite clearly. The Norman Lockyer Observatory only saw 1 of them. Armagh didn't see any of them. It was obviously in a null for those echoes. Only one of those echoes was seen in the vertically polarized system in Northwest Hampshire. So that probably was this echo here. So that echo was probably somewhat cross-polarized. So both receivers saw it. And the Malvern receiver didn't see that. Both Malvern and Armagh are seeing a little bit of a direct signal at that time. Sometimes all the receivers do see the same echoes, particularly when the tail echoes are fairly big. I think in this example you can see the echoes were seen with somewhat different shapes and somewhat different Doppler shifts, but they were seen by all of the 5 receivers that are operating, but only one of them really saw a very vestigial head echo there. But data for that head echo is available in the system. It's just not practical to show it in this display. Excuse me. Now we see some pretty strange echoes that need a bit of explanation. These U-shaped echoes that we see quite often are described as epsilon echoes. And I would suggest that this is an area that needs some more research. What is going on in the ionosphere that is causing these echoes? Is it the meteor breaking up, or is wind shear involved? And there are all sorts of interesting questions that can be explored. Here's some more examples with multiple tail echoes, perhaps suggesting the meteors pass through a region of the ionosphere with different pre-existing levels of ionization and with different wind velocities, giving the spread of different Doppler shifts that we see. And this is beginning to show the system, how the system could be a valuable tool in studying the interaction of meteors with the ionosphere. So, summarizing phase 2 of the project, which is nearly complete, we have up to 6 receivers input to the project server, a 6-screen display showing low resolution but nonetheless interesting outputs from the 3 receivers, and we will have streams of precision data available for research and development. And the final phase is when we will be developing, of phase 2, is when we have the means of triggering on events. All the screenshots that you will see tonight, I think, are ones I've captured just randomly by having the receiver display running on a second screen. When I see something interesting, I grab it. So they're not the result of systematic observation. Hopefully systematic observation will be done by people using the system, but to make life easier, we plan to implement a system of event triggering and capturing of recordings of interesting events. We will have rolling buffers for each receiver, and when any receiver receives something that looks like it's a meteor, we'll capture that information and save it away for further analysis. And that's where the timing information that's in the raw data is very important, because we can then correlate those observations from multiple directions. Obviously the trigger mechanism has got to be able to distinguish meteor events from interference, aircraft, etc. And that's what we're working on at the moment. That's Andy G4JNT has been working on that part of the project. Just going back briefly, this is again the timing streams. Here's a very long-lasting head echo, tail echo. Excuse me. And that kind of data will be the kind of thing that we will be capturing. I thought it'd be interesting to look at some of the echoes from the recent Perseids shower. There was plenty going on. And again, we're seeing some of these interesting epsilon echoes, and it won't be long if you go to the live stream at the project website. It won't be long before you see something like this. It's best to go in the morning UK time, or the first part of the day from midnight to midday, because that's when the Earth is facing into its direction of travel around the Sun, and therefore colliding with the maximum amount of material. Of course, it's not quite the same when we're in a recognised shower. Other times may be more fruitful. You see there's no shortage of these strange echoes, strange epsilon effects, echoes with multiple tails, and in this case seen by all 6 receivers. I think I've been guilty here of only putting into the display here some of the weirdest echoes. You do see more normal ones, like the classic echoes with a head and a tail that I showed you earlier on, but I think the reason for doing this is to show there's plenty that we don't understand that needs further discussion, and I think a particular value will be when we are able to compare the radio events and these weird displays with optical observations, and that's something which we very much look forward to doing. So that's where we're headed with the project. This is the team, basically. We've got John Berman, the webmaster. I'm sort of notional dog's body, but all the others have contributed in multiple ways. Dave has done a lot of the work on the Pi. Nigel Cunnington at the Sherwood Observatory has supported us there with the beacon. Mark has been helping with the web interface and so on. Dave is the contact at Norman Lockyer Observatory. Andrew from the Radio Astronomy Society. Heather is our principal software designer for the server systems and so on. And Dave has been is the person who's built the independent receiver at Malvern. And Andy, who many of you in the radio world will know, was the prime mover behind the beacon PA and the recognition software. So I think that's about it. If anyone has any questions, I shall do my best to provide a plausible answer.
Lovely, Brian. Thank you very much. And of course, we'll put those the links. I think we put one link in particular, and we'll make sure we put that on the RSGB website, a recording of this live event as well, for anybody to be able to click onto and watch later. So if you have any questions or comments you'd like to share and haven't already done so, please do so now on either YouTube chat or BATC messaging. And please don't forget to include your first name and your call sign if you have one as well. Brian, I mean, it seems to me obviously lots of radio amateurs involved with this. Are you looking for others to join in? How can people watching this join in?
I think there's a number of ways. One of the ways which we haven't exploited to the full is the STEM potential of the project. I've found when running events such as in British Science and Engineering Week, that when you run a display showing the meteor echoes, people are absolutely fascinated by the frequency with which meteors are impacting Earth, and the fact that you can actually display it in all weather conditions using radio. So that's one area where I think we could do a lot.
Can I just, Brian, sorry to interrupt you there, but just for those not maybe aware of a modern phrase of STEM in terms of education, it stands for science, technology, engineering and maths, doesn't it? It's about bringing those together into practical things. I just wanted to make sure everybody at home realised what the STEM meant.
Yeah, absolutely. And making a meteor receiver, you're going to learn about a number of things to do with radio, some things to do with astronomy, some things to do with electromagnetic compatibility. The bane of all radio astronomers is man-made noise, and you'll discover a little bit about that and how to live with it or defeat it. So yeah, that's great. And I think now we're looking for people to use the data that we will be making available on the live streams for serious meteor research.
Yeah, thank you. I mean, actually, Lewis, I don't have anything. Radio Lose says, as an active STEM ambassador, this project is a godsend. Thank you. There's many other people, of course, saying thank you as well, Brian, to all the work you're doing. Surrey EARS says, thank you for the interesting talk, Brian. This has definitely motivated us to build our own receiver to tune into your beacon here at the University of Surrey. So a link to that question as well. Are the receivers, the design of it using the Raspberry Pi and the SDR Play and things, is that an open source design that you can help people make their own?
Absolutely, you can make a simple one using sort of any of the cheapo SDRs. But if you want a really good system, the answer is to use a slightly better system, better receiver, and better antenna. The intention of the project is that everything will be open source, and I believe, although I can't say exactly what, certainly anybody who asks me, I'm happy to provide block diagrams and so on, and some of the software is already on GitHub. The software for the receiver is largely centered around the BATC, that's the British Amateur Television Club, Portsdown system, which is thoroughly documented. Kits of parts are available and so on. If you build a Portsdown, that's really what the system is based on. So there's already a lot of material out there. I would say that we're guilty of not having organised it into its ideal format, but we can just say go to this one site and do it. But certainly if you look at the Portsdown system, that's very well documented, and we can provide any other information that's required.
Yeah, so thank you, Brian. And as I said, we will be putting a link to the project on the RSGB website shortly after this, when the recording of this programme goes out as well. If you've got any questions or comments or anything else at home, if this has inspired you to give it a go, please make a note of it now and let us know on a BATC messaging or YouTube chat. Someone who's done that is Gary Hurd, M1BOA, who says our Astronomical Society, North Norfolk Astronomy Society, are running using Graves at 143.050 megahertz, but he says, I think we'd be interested in using 50 megahertz. What are the sort of differences they're going to find between running on 2 meters and 6 meters?
Well, the first thing is that Graves, of course, does not provide any realistic coverage over the UK. It's located near Dijon in France, and it beams basically from east through south to west, stepping round in steps. It's unusual for it to illuminate any meteor event over the UK, whereas 50 megahertz transmitted from the Sherwood Observatory is illuminating the sky over a large chunk of the UK. My advice would be you can start using almost any receiver and almost any antenna, but Norfolk is not that far from Sherwood, so I would suggest starting make one of those Moxon antennas and point it vertically upwards. That's where the echoes are going to be coming from, and that will help minimise the direct signal from the beacon, which will be pretty strong in Norfolk, I'm sure. And those Moxon antennas, if you follow that link, it's on the bottom of the screen at the moment, is really great. It shows you for a few pounds and a trip to your local DIY store, you can make a slightly Heath Robinson, but nonetheless effective antenna. Make that, point it upwards, connect any receiver you've got that covers 50.408. It could be a software defined radio. If it is, then you can use something like SDR console to display its output. But if any receiver, you'll start hearing pings. Best time in the morning.
Lovely. Yes, you said before midday, I think. We've just put those links up again, but again, that will be on the RSGB website. You'll be able to easily click on it at home as well. Had another comment now, probably on a similar subject, from Peter G4URT, who says, Brian, when using 2 meter MS, I guess that's meteor scatter modes, I've never seen the head echo. Is this because of the higher frequency?
Yeah, no, I suspect it's because they last such a very, very short period of time, a few tens of milliseconds. They're of no interest for meteor scatter, really, because even with the finest digital modes, 10 to 100 milliseconds isn't long enough to get much data across. So I think that's why you don't see them. They certainly exist, but they're much more prominent on a waterfall display.
Yeah, thanks. Nick Everts, KC2VWR, says it would be nice to do this in the US as well. I guess he can't probably help with direct data, but are you aware of any similar projects going on in other parts of the world, including the US?
In terms of amateur radio projects, no, but I have been in touch with a few people in the States, and it's a matter of getting them together. I don't have in my mind at the moment exactly who the contacts are, but I have certainly exchanged information through the radio astronomy group, IO group. I think the contacts were made. Of course, the beacon, there's nothing novel about the beacon. In Belgium, they have 2 systems, the Brams beacons, but they're not, and they're very effective and have been going for years. But they're there to cover the area above Belgium, and you can receive their echoes. They're on a different frequencies, about 49 point something. Again, I don't have the numbers in my head. That is an academic, I think, led project. I am not aware of any other sort of amateur led projects, although there is a lot of interest. Having said that, actually, that may not be quite true. There's I'm sure there must be other ones around, and possibly Italy might be a place to look. I think there's some rumblings coming from Italy, and I've met with a Japanese amateur who visited here, and they're doing some work, not using a purpose-built beacon, but using FM broadcast transmissions. So there's a lot of people looking at echoes off meteors, but as far as I know, there's nobody particularly building a system with a network of receivers which ultimately will form what is in effect a bistatic radar system. This is what we're sort of gradually working towards. And if anybody wants to do it in the States or anywhere else, we're very happy to provide any information that they think will help. No problem with that. It's definitely open source. The problem is that when you're developing something, you're still in the development stage. You don't know quite how open to be, because 10 minutes later things might have changed. But I think we're getting to the point on phase 1 and phase 2 where it will be stable enough to say, yeah, you can go and find the software. It is already actually, I'm told, on GitHub. I have no idea how you find it, but those who are familiar with GitHub may know what I'm talking about. Sadly, I don't.
I think it's a repository of lots of software that people have written essentially and giving away to the amateur world, I believe, is a reasonable way to summarise it. But it sounds like a fascinating thing. Of course, I mean, even though I'm sure all of the amateurs involved with this are giving their time free, it must cost money to put this stuff together. When I was doing a bit of homework about this, I noticed that the RSGB Legacy Fund are supporting the project as well.
Yes, we've had very good support from the Legacy Fund. Phase 1 was building the transmitter. They funded the capital cost. The electricity bill is currently being met by the British Astronomical Association, which is great. And on phase 2, we have funding to build these 6 receivers and deploy them. They're built, and I suppose more than half of them are deployed, although not necessarily exactly where we want them to be. We are moving towards getting one in Scotland, which is very important that we get a receiver to the north, and we look forward very much to that. I would quite like to move one of the 2 receivers that's currently running, or the 3 receivers indeed, that's one of the 3 receivers I've got here will be going to Scotland. One I would like to deploy to somewhere further southeast, again to get the best varied geometry.
I mean, do you have any? I mean, you've got a lot of people watching this now, and probably a lot of people will watch the recording as well, Brian. I mean, are there particular areas of the country that you want to put a shout out to for people who might get a support putting a receiver?
Yeah, there are 2 criteria. We don't want them too close to the beacon because the direct signal will be overwhelming. Ideally, I think the ideal spot to consider after Scotland, which is currently our top priority, would be maybe the far east of Kent. So if anybody's out there in the far east of Kent, I'd be interested with a suitable site. I'd be interested to hear from them.
All right, that's a very good plug there for that. In fact, Gary, who is in the Norfolk Astronomy Association, M1BOA, says his thoughts exactly referring to making the Moxon and then point it upwards and see what we get. The SDR they're using, I think, is an NESDR Smart. So that's the one that they're actually using there. Bill, GM4UBJ, in the very area you've been talking about, does the 6-meter beacon send its identification at any time, or is it a constant carrier?
Very good question. It does in fact identify with A1A keying, and it sends it as infrequent as I think I can get away with, and as fast as I think it can get away with, which unfortunately produces some slight key clicks, which I think are described somewhere in the documentation on the website about using the live stream. Yes, I would have much rather it didn't have to identify, but the quick answer is yes, it identifies, but ever so fast and as infrequently as I think I can get away with. So far, nobody's complained.
I'm sure. Brian, it's been a wonderful evening again and getting an update in your project. I'm going to leave the last words from our audience at least to Terence 2E0IPK, who says, just shows what an amateur radio license opens the door to so many great projects. Thank you. And lots of other people saying thank you and an excellent presentation as well. And I echo that, of course, on behalf of everybody else. Brian, thank you very much for joining us tonight, and we can't wait to find out what phase 3 is as well. In the meantime, we'll put that information up there and hopefully you'll get many other followers of your project. Thanks once again.
Well, thanks everybody for coming. Thank you.
Thank you. There we are, and that does conclude this webinar. And thanks once again to Brian Coleman, G4NNS, for tonight's presentation. You can also watch his original presentations on the first phase of the project on the RSGB YouTube channel. Well, the RSGB convention is a great place to learn new things and meet many other like-minded people. Hosted centrally near Milton Keynes, this year's event is now just 6 weeks away, but you still have a chance to book your place at early bird prices. Details of the 2024 convention activities and talks, which this year are organised into 3 streams of getting started, operating and technical, can all be found at rsgb.org/convention. Captions at the bottom of your screen now. Well, we hope you've enjoyed this Tonight at 8 and that you'll be able to join us next time when Ian White, GM3SEK, will be joining us to give a hitchhiker's guide to aircraft scatter. If I had meteor scatter, next time it's aircraft scatter. This is the technique of bouncing amateur VHF and UHF signals off aeroplanes. If you'd like to see details of future webinars or watch recordings of previous programmes in this series, please visit us at rsgb.org/webinars, where you can also send us comments and feedback. And if you subscribe to the RSGB's YouTube channel, you'll be notified of all upcoming Tonight at 8 webinars, as well as other new videos and presentations from the Society on a wide range of amateur radio topics. Thanks for joining us this evening, and until next time, this is David G7URP signing off and clear. Bye-bye.